All right, let's pray and we'll get started. Heavenly Father, thank you for today, and for those who are able to be here. Pray that this be fruitful for us, that we remember the things that we've been learning and be prepared to move forward. Those who are watching online or will catch this later, Father, I just pray that you be with them, help them to have clarity of thought, and help me to teach in a way that everyone's able to receive this. Pray in Jesus' name. Amen. All right, well, I want to start with the off-bow principle. Do you remember that German word? Yeah.
I remember that you said the word.
Yeah, remember that I said the word. So it's this idea of orbital filling. What order do things happen? Okay. Do you remember the first one that gets filled? What is it?
1s.
1s, right? And what's next?
1s. 2s.
2s. What's next?
2p.
2p. Okay, what's next?
3s.
3s. And then?
3p.
3p. And then?
4s.
4s. And this is already setting for us the pattern that ultimately we're going to be following. They fill in this direction. Okay. So what's after my 4s?
3d.
3d. And next?
4p.
4p. And next?
5s.
5s. Okay. So again, I've got this action happening. All right, what's next after 4s? Or 5s, sorry.
4d.
4d. Okay, what's next?
5p.
5p. And next?
6s.
6s. Good. What's next?
4f.
4f. And then
5d.
5d,
6p.
6p, 7s. Right? Then I come out here and I've got
5f.
5f,
6p.
6d, 7p. Right? Okay, so that completes it, right? Good. Now, how many electrons fit in the s orbitals? 2. And in the p orbitals? 6. And in the d orbitals? 10. And in the f orbitals?
14.
14. Good. This first number, 1, 2, 3, 4, 5, 6, 7. What is that? What quantum number is that? It's your principal quantum number. It's your in number.
Should be 1.
Oh, I'm sorry. I'm saying, like, what is it called? What is it? If I say 1 or 2 or 3 or 4 or 5, which of your quantum numbers is that? That's your first quantum number. It's your in quantum number, your principal quantum number, right? Give me the 4 quantum numbers. We got principal, right? In.
N.
And then what else do we have?
L.
L. And what's next? Huh?
ML.
M sub L, and then
M sub s.
M sub s. Okay. So n is my principal quantum number. Let's just say which orbital, which level are we in, right? And then L is referring to my geometric shape. S orbitals are spherical. P orbitals are dumbbell shaped. D orbitals get crazy. Not touching those. And then forget the F. Okay. Then what's happening in the L, or the M1?
It's the magnetic. Where it is in space.
Yeah, is it the magnetic, or is it the, is that what you have there, is it magnetic?
Yeah.
Okay.
M.
Okay, what do you have for MS?
Spin.
Okay, and then spin. And what do you have for a description for your magnetic quantum number?
Orientation.
It's your geometric orientation, right? Orientation in space. And this one is spin. It just means, is it spinning up, or is it spinning down? Is it plus 1/2, or is it minus 1/2? Okay, I want to pick one. I want to go, get your periodic tables out. We're going to do one real quick. Oh goodness, I've just got stuff everywhere. I've got a periodic table. Let me pick one. Let's go, let's do titanium. Okay. Oh, I'm sorry. Let's do thallium.
Okay.
Thank you. Thallium, what's its atomic number?
81.
81. Okay. What kind of an element is it? Where is it at?
Metalloid?
Isn't it?
Yeah, it's a-
Yeah, let's go with the name. Let's go with it. Let's go with gold. Let's do gold. Atomic number?
79.
79. What kind of an element is it? Where's it at?
Metal. Transition.
It is a metal. It's a transition metal. It's in which block?
11. What?
You're in which column? I want to know which block it's in. Is it in the S? Is it in the P? Is it in the D? Is it in the F? Look at where it's at. It's in the D. If you think about your periodic table there, right? You've got, this is your S, right? This is your P, this is your D, and then the other is separated is your F, okay? Gold is located what, somewhere about here?
Yeah.
Okay, so it's in your D block, it's a transition metal. So it's already filled its S and now it's working on its D, right? So that's just a good thing for us to think about what we should expect to see here. So it's atomic number 79. S's hold 2, P's hold 6, D's hold 10. Let's keep a count here. What's give me what you got. 1s
1s.
2,
Yeah.
2s 2,
2p.
2p 6,
3s2.
3s 2, 3p 6,
4s2.
4s2. What's next?
3d10.
3d10. Okay, what's next?
4p6.
4 what?
4p.
4p6. Okay.
And then 5s2.
5s2, and then now what?
4d.
4d,
10.
huh?
10, I think.
10. Let's do a quick count. 2, 4, 10, 12, 18, 20, 30, 36, 38, 48. Right, so we've got a little ways to go.
Yeah.
Okay. 4d10, what's next?
5p.
5 what?
5p. 6.
5p6.
6.
What did I say we were at?
48.
We were at 48. Okay, so now we're at 54. Okay, 5p6, what's next?
6s.
6s. 6s2. Okay, that puts us at 56, right?
Now it's 4f.
Now what?
4f.
4f. Okay, how many does it get now?
14.
That's 14. Okay, so that puts me at 60, that puts me at 70, and what's next?
Now it's 5d.
5d,
9.
D9. Right, that makes sense. That's a hard one, right? All right, how many valence electrons does it have?
9.
Define valence.
9 is the last. Okay.
Define the valence electrons.
Like the free electrons on the last shell.
They're the ones in the outermost shell. What's its outermost shell? Which of these is its outermost shell? Look at the principal quantum numbers. 6s, 2. So it's got 2. Okay. All right. Well, good. All right. Give me all of this in a very simplified format. Do you remember how to do that?
Yeah. Xenon.
xenon, right? So whatever xenon has, Xe, okay, and then to xenon is, what's its atomic number?
54.
54, so it was right here, so it was this one, right?
Yeah.
Okay, good. So I can write xenon 6s2, 4f14, 5d9. Good. Okay, life's good. All right, let's move forward. Let's look at some periodic trends, okay? There's a couple of these we need to know. This is the very end of this chapter, and then we'll start the next chapter. The next chapter that we're starting will be the last one we get to this semester, okay? It's on just bonding and on molecular geometry, which is, I think it's fun. I like molecular geometry. We'll play with balloons next class. I think next class, we'll see how far we get this to. Okay. Let's do atomic radii. Basically, this is just the subject of how, if you're looking at the valence electrons, how far they are from the nucleus, from one end to the other, how big is it? And there are definite trends, okay? I'm going to show you the trends, and I'm going to show you why for the trends, okay? So if this is our periodic table, okay? Well, just think about this. Every time I add, you know how big, you don't need to know how big, but here's hydrogen. Well, now if I fill that 1s and now I go to the 2, I've got everything that was in the 1s and I added a whole other layer, right? So you know that this is going to be bigger, right? Lithium is going to be bigger than sodium, or than hydrogen, and sodium is going to be bigger than lithium. And in fact, that's true all the way down the periodic table. I don't care where we're at. As I move down, it's going to get bigger, okay? That's intuitive, that's expected. Here's the one that's not expected. You might think, oh, I'm adding electrons, so I get bigger as I move across, but we don't. We actually get smaller as we move across. And I need to explain why. There's this thing called a Z number, right? Z is the nuclear charge. So Z, the nuclear charge is going to be positive. It's coming from the protons that are there in the nucleus. But the only electrons that experience the full nuclear charge are the ones found in hydrogen. Because there are other factors at play that influence the effect of the nuclear charge. So hydrogen has just got one proton, one electron, but when you put in helium, it's got two electrons. Now you think Pauli exclusion principle, they want to be away from each other. So they're going to push out a little further. The nuclear charge wants to draw them in, which would bring them closer to each other as they get close to the nucleus, but they're also repelled from each other, so that gives them a slight push out. Okay? So Pauli exclusion principle and the fact that they want to repel each other causes them to be further out than you would expect just based on nuclear charge. So there's this other concept. Besides nuclear charge, there's this Z effective nuclear charge. Okay? So what's the overall effect of the nuclear charge? Well, this is a matter of nuclear charge and what we're going to call shielding and Pauli exclusion principle. remember, this is the only one that gets it all, okay? Shielding is far more important than, is a factor than Pauli's exclusion principle. So here's what we're saying. Let's look at lithium. Okay. So lithium has 3 protons, 3 electrons, yes? So I got 3 positive charges hanging out in my nucleus. Out here I've got 2 electrons in my 1s shell. And I've got 1 electron out here in my 2s shell. When I talk about shielding, what I'm saying here is this electron is shielded from the full effect of this nuclear charge by the interaction of these electrons. At the right given time, this electron may pass in front, and it's taking the brunt of the nuclear effect, and at the same time, it's due to exclusion and like charges repelling, it's pushing this one, has a slight push away from it. So this one doesn't experience as much of the nuclear effect because of the electrons that are present in the shells below it. Okay? So shielding is really referring to about not so much other electrons in the same principal quantum number, but electrons in lower principal quantum numbers. Okay? So I'm going to write that from electrons in lower in numbers. Okay? This matters. It means that lithium is a little, it's bigger than hydrogen, but it's a little smaller than we might expect just based on the mathematics of hydrogen. It means that sodium is bigger than lithium, but it's again not as big and much bigger as we'd expect based on the mathematics of hydrogen. But it really matters when we go across. So let's look at, let's do oxygen. Okay. Oxygen is atomic number 8. Right, so 8 protons, so 1, 2, 3, 4. Let's do something a lot bigger. Let's go bigger than oxygen. Oxygen is not big enough for this, to really get the idea. Let's go, iodine. What atomic number do you have for iodine? 53. Okay, so 53 protons, that's pretty big. My electrons, I got 2 in the first, right? I got 8 in the second. And then I've got, how many in the next one?
8.
How many fit in the third total?
10.
18, right? 10 and 8 and 2. 18, right? So 18 electrons. Okay. I probably should have picked one simpler than iodine. I should have planned my strategy earlier. What's after the, what element am I up to here? I'm up to argon. Then I keep going to krypton. It's going to take too much to go this way. Let me start this over. Bear with me. We'll go back to oxygen. Oxygen has 8, right? 2 in the first. And how many in the second? 6. Okay, what's next after oxygen? Fluorine. Fluorine has 9 protons, so I've added more effective nuclear charge. Have I added more shielding? How many are in the first? 2. Only 2. So I've added more nuclear charge, but I've not added any more shielding. I don't have any more in between these outer electrons and the inner electrons, right? So more nuclear charge, less shielding should mean that they stick closer, right? which means I'll have even though I've added a proton, I've actually decreased its atomic radii, or radius. So 1, 2, 3, 4, 1, 2, 3. Okay. And then over here, as we do, what, neon? Right, neon's gonna have 10, 2 in the first, and then 1, 2, 3, 4, 1, 2, 3, 4. I've increased, again, my nuclear charge, but I've not increased my shielding, therefore it's going to be tighter still. So the pattern is that as I move from left to right, I increase my nuclear charge, but do not increase my shielding, therefore I decrease my radius. Okay, so it's counterintuitive. So overall, if somebody were to say, hey, I want you to draw just a sketch of the periodic table and show me one single arrow that represents atomic radii and the trend, you need to have this. Okay? Move your largest is here. Okay? Your tightest, your smallest are up here. Your book has some diagrams of that. You're not looking at your book. You saw a video. I'll show you the video in a minute. We don't need to be in that big of a hurry. All right, let's do which of these has put these in the right order? GE, FL, BR, KR. Okay. Which of these is the largest? Which is these is the smallest? The most important thing to look at is your principal quantum number. 1, 2, 3, 4, 5, as far as its valence electrons. And then I want to look at from left to right. So if I have two of them that are both like n equals 3, then the one that's furthest left is going to be the biggest, the one that's furthest right is going to be the smallest. I could have one that's n equals know that. You want to go, first of all, with your principal quantum number, and then you want to move left to right. So take a look at that and see what you get. FL is thorium, element number 114, by the way. It's not for fluorine, which is F. You guys find them all on the periodic table? It's the largest one.
So how long is it? Fi?
FL. Well,
FL?
looks like it's FL. What do you got? Let me see what you got.
We're trying to find FL.
Oh, okay.
Find GE, ER.
What's it? It's 118. Or no, I'm sorry, what is it? Yeah, it says,
114.
it says 118.
It's 114.
114? Okay, they literally have, all right, 114. Nope. I don't know. Go with number 114. Let's do that. This is number 114. How about this one? How about GE? What is it? What number?
32.
32 and BR?
35.
35 and KR?
36.
36. Well, I can tell you 32, 35, 36. Which one of these is the biggest?
32, 32,
32, followed by
35,
35, followed by
36.
36, right? If I'm getting bigger, right? Then my only question is, where does 114 fit?
I think it's bigger.
Should be bigger because I'm moving down, right? I'm going this way. So 114 would be here. So then my order here is FL, and then GE, and BR, and then KR. Okay? All right. Let me ask you another one. Obviously, I don't have a copy of the periodic table on me. Which is going to be bigger, cesium or calcium? Far left, towards the bottom. Cesium's going to be bigger, right? It's down near, it's almost as big as they get. Which one's going to be bigger, nitrogen or carbon? Carbon, right? It's further to the left. Which would you expect to be bigger? Helium or lithium? Lithium has a larger principal quantum number. Okay, very good. Let's do the next one on here. Let's do, ionic radii. Okay. I don't like this one. Let's look at this. Let's still look at oxygen. And oxygen -1. And oxygen -2. What's my Z number for each one of these?
It's
8. 8. How many electrons in the first for each of these?
Wait, what?
How many electrons in the first for each of these?
2.
2. Okay. How many electrons in the second for this one?
6.
6. How many for this one? 7. How many for this one?
8.
8. I have here the same Z number for each one. We're not adding any protons whatsoever. We're only adding electrons, right? We're not adding any shielding at all whatsoever, right? The only force that's going to affect this is repulsion, right? So as I add more and more electrons across this, it should get bigger and bigger and bigger slightly, right? This is not even as significant as looking at elements, different elements with the same electronic structure. We refer to these as being isoelectric elements, or isoelectric ions. Okay? So let's look at this, isoelectric ions. So for instance, let's do carbon, and let's do nitrogen, and let's do oxygen, and let's do fluorine, and let's do neon. Okay? Neon has how many total electrons?
10.
10. So if these are going to be isoelectric, I want all of these to have 10. That means this is going to be fluorine, -1 charge, oxygen, -2 charge, nitrogen, -3 charge, carbon, -4 charge, right? Okay, now this one has 6 protons, this one has 7 protons, this one has 8 protons, this one has 9 protons, and this one has 10 protons. Okay, so the question is, which of these ions is going to be the largest? We can go further. What comes after neon? So let's stop. I don't want to go too far for me or for you. So these guys are isoelectric. All right. In this case, I have an increasing Z number, right? So Z is going this way.
So that one is bigger. Carbon is bigger.
Carbon has much less, and yet it has more repulsion. So in relative size, I'm just going to draw this. Carbon is going to be pretty huge.
Yeah. So clever.
Yeah.
Okay, does that make sense? So we're dealing with isoelectric. As I add electrons, but I don't add nuclear charge, it goes this way. Okay? All right. If you think about your periodic table, right? Well, if I add a principal, I'm taking away your outermost here, right? Hydrogen, lithium, sodium, etc. Move it as I move down, but I still, the principal quantum numbers are still larger as I move down, right? So atomic radii are going to be bigger moving down because I've got electrons further out, right? The other trends do not necessarily remain the same, okay? We want it, like I said, we want to be concerned with ones that are truly isoelectric. And also, again, as you look at oxygen, if it's oxygen neutral, oxygen -1, oxygen -2, thinking how many electrons it's picked up. The more electrons it's picked up without changing its nuclear charge, the larger it's going to be. That is the principle that we want to have there. What do they want to ask you on? What kind of things you need to know for something like that? Do they even ask you one? You just go straight into ionization energies. All right, let's look at ionization energies. Make a title for that, okay? So this is how much energy does it take to remove an electron? Okay. Draw my periodic table again. which of these most readily will remove an electron? To the left or the right? To the left. These are the easiest, right? It doesn't take a ton to remove an electron from these. Only think about something like sodium. If you put it in the water, what does it do? Pardon? Well, no, it doesn't dissolve. It's explosive. Okay.
It's not sodium.
Something like helium helium has a full valence shell. It also has a full, if we were to draw helium, right, it's got 2 protons, 2 electrons with no shielding. These things are held so tight, so tight. This one does not, this is the hardest one to ionize, okay? The effects of shielding means that as you move down your quantum numbers, there's less of a hold on each individual electron in the valence shell, therefore it's easier to get rid of that electron, right? So there's a certain amount of energy that's required for hydrogen, but I take hydrogen and I put it in water, it's not explosive. I put something like sodium in, or potassium, rubidium, cesium, francium. The farther I move down, the less hold it has on its electrons, right? So if this is the hardest, this is the easiest. You can already see the trend, can't you? We move this way. Question? All right. So ionization energies, it takes less energy as we move up, and it takes less energy as we move across. This way, because of the N number.
Less energy or more?
Doesn't it take more energy to
You're just thinking about what I'm saying backwards of how I'm saying it. We're thinking the same thing, but we're saying it backwards, right? The smaller the N number, the greater the hold it has on its valence electrons. Okay? Makes sense? Because there's less shielding. Okay? And same thing moving across, there's less of an effect due to shielding. Okay? All right. There's some variations to this. We're not worried about that. If it comes up, you'll be able to get it.
We got some work. Maybe about the temperatures the first time. So stuff like that. And here in their heavy class, I think kind of people headed science, sorry, your natural sciences, anything like that.
All right. Variation in electron affinities. Let's do electron
A
affinity.
lot of the non-science, like started galaxies, that's something a little bit more enjoyable, something like chemistry or anything, but started galaxies set up and everything. We don't necessarily need the science knowledge, but science.
All right.
Here
All right. What do you need to know about electron affinities? We define electron affinity. Electron affinity is the energy change for the process of adding an electron to a gaseous atom to form an anion. Okay, so how much energy does it take for this thing to accept an electron? Okay. Is that really how much the process can be? Form a negative ion. All right. So which one is going to be the least receptive to receiving an electron? Helium. And the most receptive? Okay. probably about as much as I'm going to want you guys to know about those is what is the trend, okay? So if I'm looking for a trend for atomic radii, remember we go from small to large, moving diagonally. My others are moving diagonally the opposite direction in terms of energy, right? And then the other one is the ionic radii, and there we just have some principles that we're trying to hold on to. What do we have for time? This always takes longer than I think it should.
It's one time.
Got 30 minutes.
Good. Okay. I'm going to make use of it. All right. So this is a new chapter. Okay. This will be chapter 7. All right. So we're looking at bonding now, right? Have I shown you guys this before? Okay. So this is difference. We talked about electronegativity. What is it? It's the ability to attract electrons. Okay. So this is the difference in electronegativity. So it's the difference. So I've got two atoms. Each of them have an ability to attract electrons. If I have two hydrogen atoms, is there any difference in their ability to attract electrons? No, they have the same. It'd be like twins, right? Like they look the same. Good luck picking one based on appearance. But if I have two that are different, they're going to have different electronegativities. There's going to be a difference, and so electrons will be attracted more towards one than towards the other. We're going from, hey, these have, on this end we have no difference, so these are atoms that are the same, okay? Like identical atoms, all the way to ones that are very, very different. And so the type of bonds they'll form, the characteristics of those bonds are very different. When I have an extreme difference in electronegativity, I'm going to form an ionic bond. When I have no difference, I'm going to form a nonpolar covalent bond. And when I have a slight difference, I'm going to have a polar covalent bond. The dividing line here is about 0.4 difference. Okay? The dividing line on the other, I'm going to have to look up because I don't have that one memorized. He gives it to us. Ah, 1.8. I don't know that you have to have these numbers memorized, okay? If I decide later you do, I will tell you that. But okay, it's the idea that if I have a slight difference, very slight, then it can form a nonpolar bond, which is basically saying those electrons are shared evenly. Okay? The greater the difference, the less they're shared evenly. The more they're attracted, they hold around one atom than they do the other. And eventually, if the difference is so great, they don't bond covalently going around both of them at all. They separate, They'll stay around one, and they won't be around the other, and then I have an ionic bond, and that difference is 1.8. If I have 1.7, I'm just in a very, very charged polar bond. For instance, oxygen has an assigned value of 3.5. If I bond that with oxygen, what's the difference?
0.
0. So what kind of bond am I going to get?
No polar covalent.
It's going to be a non-polar covalent bond. If I bond it with nitrogen, which has a 3, what kind of bond am I going to get?
Polar.
Polar, because the difference is
0.5.
0.5, which is greater than 0.4, therefore I'll have a polar covalent bond. If I bond it with hydrogen, which is 2.1, right, what's my difference?
1.4.
1.4. It's getting close over here to this line, to this limit, right? And so water, H2O, is a very polar molecule, right? It's like, it functions like a magnet, has regions of some serious charge. If I bond oxygen with lithium, 1, what's the difference?
2.5.
2.5, what kind of bond is it going to make?
Ionic.
It's going to make an ionic bond. Does that principle make sense? Okay. All right. Good. I don't know why they don't teach it like that in the book, but they don't. That's all I have to think about it. Let's go back. Ionic bonds, ionic compounds. It says here the properties of ionic compounds shed some light on the nature of ionic compounds. Since ionic solids exhibit a crystalline structure, so these are ionic solids. I do want you to know this, okay? Write this down. They form crystals. They're rigid. What does the word rigid mean? What's the opposite of rigid?
It's soft.
Huh?
Smooth.
No, well, not necessarily smooth. You said soft. How about flexible? These are
Malleable.
malleable. Yeah. So the idea of rigid is like this thing does not move. Okay? So it's rigid. Well, if something's rigid, what happens when it does get moved too much?
It breaks.
It breaks, right? So it's rigid, but it's also brittle. This thing doesn't just bend at all. They also tend to have a high melting point and high boiling points. So for instance, table salt, you go to heat, if you had a pan of table salt, that's not going to melt. Not at the temperature you can get it at. You take the same pan and you pour sugar into it, it'll melt, right? That's how you form caramel. Good luck melting sugar, it's not going to, or melting salt, it's not going to happen. Right? Ionic solids, you can melt them, but it's very, very high melting points, very, very high boiling points, right? Melting point is to go from a solid to a liquid, boiling point going from a liquid to a gas. All right. As a solid, they don't conduct electricity well. But they do dissolve easily in water. And in their aqueous form, electricity well. All right. This concept of a binary ionic compound, tell me what that's going to mean. Just two. Name one, you know, this famous one. Talk about all the time. Table salt.
Table salt.
NaCl, right? Okay. It's going to have an anion and a cation, right? Anion is going to have what charge? Positive or negative? Negative. Cation is going to have a positive. Okay? So my cation is going to be my sodium, my anion is going to be my chlorine. Okay. Types of, where would I expect to see these form? What's going to form ionic compounds on your periodic table? Which two things combined? Which two types of things combined?
Well, I don't know the types, but usually from group 1 to 3, when they go from group 5 to 8.
Okay. So somebody take that a step further. The concept's right. What do we call the ones he mentioned and the other ones he mentioned?
There's a no metals.
Non-metals with
Metals.
metals, right? So metals and non-metals. And if you look at this, my cation on here is a metal. And my anion here is a non-metal, right? So that's it. Whenever I have this combination, I would expect to have a difference in electronegativity greater than 1.8 or whatever it was. That's that threshold to form, okay? That's always going to happen. All right. Okay. Let me read this to you. The formula of an ionic compound represents the simplest ratio of the numbers of ions necessary to give identical numbers of positive and negative charges. For example, the formula of aluminum oxide, Al2O3. Indicates that this ionic compound contains 2 aluminum cations for every 3 oxide anions. Right? So, aluminum, take a look at where it's at on your periodic table. What charge is it going to have as an ion? Plus 3. Oxygen, what charge is it going to tend to take? Negative 2. My total charge here is plus 6. My total charge here is negative 6. Those charges balance, right? So it's saying whenever I see this kind of a formula for an ionic compound, I should expect to see my charges balanced. Okay. It's important that we note, however, that the formula for an ionic compound does not represent the physical arrangement of its ions. So I'm not just going to have 2 aluminums hanging out near each other, and then 3 oxygen atoms hanging out near each other, or ions hanging out near each other. It is correct to refer to sodium chloride. It's incorrect to refer to a sodium chloride molecule because there is not a single ionic bond per se. So if I talk about NaCl, it's not like these two are just attracted to each other, exclusive of everyone and everything else. Remember, these form in a crystalline structure, right? So three-dimensional. I have Na and it's a positive charge, and Cl it's a negative charge. What should I expect to see also near this Na? If I'm going 3D and building a crystal, would I expect to see another sodium next to it?
No.
No, because they're going to repel, right? I expect to see a Cl, right? And a Cl. And a Cl. And I'd expect to see an Na. An Na. An Na and an Na. Right, if I were looking at this 3D, right, then on this other side, I would expect to kind of see an Na, and Cl, 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 Na. You know what I mean? 3D moving out. And so it's not like this sodium is paired up with this chlorine. It shares a force of attraction with every negative charge there. It's functioning like a magnetic field at this point, rather than like a covalent bond where it's actually sharing electrons. There's no sharing of electrons here, right? This is merely an electric force of attraction. The attractive forces between ions are isotropic, the same in all directions, meaning that any particular ion is equally attracted to all of the other nearby ions of opposite charge. This results in ions arranging themselves into a tightly bound, three-dimensional lattice structure, hence crystal, right? Sodium chloride, for example, exists as a regular arrangement of equal numbers of sodium and chlorine ions. All right. Let's do this question. There are at least 14 elements categorized as essential trace elements for the human body. They are called essential because they're required for healthy body functions, trace because they're required only in small amounts, and elements in spite of the fact that they are really ions. Two of these essential trace elements are chromium and zinc. Okay, so Cr and Zn. They're required as Cr3 plus and Zn2 plus. Write the electron configuration of these cations. So writing back stuff from last chapter. And by the way, use the simplified method, right, where you're going to have this. So in this case, if I were looking at chromium, I could look at the regular electron configuration for chromium, right? But what's going to be the difference between this cation and the regular chromium atom?
Last 3 electrons.
Yeah, we're going to take away 3 electrons, right? And in the case of zinc, take away 2 electrons, okay? So find where they're at and tell me what this should be.
Physical gases. I'm gonna do
Chromium is atomic number 24.
Yeah.
Normally it'd be 1s2, 2p6, 3s2, 3p6, 4s2, 3d10. It's probably more than I need. It's chromium.
So you put our number 4s2,
3d4. Is that right? Let's add those up. 2, 4, 10, 12, 18, 20, 24. That'd be right for chromium, but what ion do I need? Plus what?
plus 3.
Plus 3. So what do I do here?
You take 3,
3d1.
1.
That's what that would look like. Get that? Good. And what's my other one?
Zinc.
Zinc. What's my atomic? Oh, atomic number
30.
30. Okay. So it's going to be the same. $3d10. Okay, but now I need a plus 2 ion. Is that right?
Yeah.
Okay, so it's going to be 3d8. Right? Good. What do we have for time? All right, let's go. You don't need that. Most monatomic ions form when a neutral nonmetal atom gains enough electrons to completely fill its outer s and p orbitals, thereby reaching electron configuration of the next noble gas. Thus, it is simple to determine the charge on such a negative ion. The charge is equal to the number of electrons that must be gained to fill the s and p orbitals of the parent atom. Oxygen, for example, has the electron configuration of 1s2, 2s2, 2p4. Whereas the oxygen anion has the electron configuration of the noble gas neon, 1s2, 2s2, 2p6. The 2 additional electrons required to fill the valence orbitals give the oxide ion the charge of -2. Great, okay. Now it wants us to do a problem with that. Selenium and iodine are 2 essential trace elements that form anions. Write the electron configuration of these anions. So we've got selenium, and we've got iodine. So this one is, the thing is with the metals, guys look, especially with the metals in the D block, they can do some funny things with shifting electrons out of their d orbitals. But with your non-metals, they're just going to try to fill. That's it. Okay? You don't have to worry about funky things happening in multiple different oxidation states and whatever. Selenium, take a look at where it's at on the periodic table. Just based on what you've heard so far, you expect it to be over on the right, right?
Yes.
It's below oxygen and sulfur. And so, how many does it have in its p orbital? Normally?
6.
No. 4. Right? It's going to be 1, 2, 3, 3p6. Or 3p4. It wants to get to 3p6, so what's the charge going to be on selenium?
-2.
-2. Okay. Iodine. Take a look where iodine's at. It's below fluorine, chlorine, and bromine.
3p5.
So how many electrons does it want to pick up?
1.
1. Okay. So now I want you to write the electron configurations for these. What's its previous
Argon.
argon? So you can go argon. Right, and then you can just start adding from argon, 4s2,
3D,
3d10, 4p what?
6.
6. Should be right. Yep. Okay, and now let's do it for iodine. Iodine looks a lot like krypton. Now I'm going to go, what, 5s2? What was that first?
Yeah, 5s,
5s2, 4d10,
4D,
5p6.
6.
Okay. Good? Good, good, good. All right. Let's do one more. It wants this for phosphorus as an atom and for phosphorus as a negative ion. So take a look at where phosphorus is at. It's down below nitrogen. Say it again. Its negative ion is going to have how many? 3. 3. Good. Now, its previous noble gas is going to be neon, right? So I can go neon, and then, was it 3s?
Yeah,
3s2, and 3p what? 3?
3p3. And for the other one, 3p6.
And for my other one, it's going to be neon, 3s2, and 3p6. Okay, very good. All right, covalent bonding. This is where they introduced electronegativity. Show you the trend for electronegativity.
I didn't meet with the trainer.
Get out, what are you even doing here?
I didn't meet with the trainer. I just thought it would come in case I missed anything that really important.
You missed like an hour and a half.
Yeah.
Did you have a great sit down?
At least I came. At least I could have not come.
2 minutes.
You couldn't have scheduled your training session for?
Yeah.
Don't even answer. I don't want to
When
hurt
she
my
parts,
heart.
I come because she never comes in. So whenever she's in, I come.
You have to just do it. Oh my. All right. Tell her to tutor you in chemistry. All right. Oh my. Go watch this at home, okay?
Yeah, I will.
Yeah. All right. So here's our periodic table. So which one is going to be the most electronegative, the most attractive to ions? Which one's going to be the least? Well, we're going to ignore these, okay? These don't want to bond anyways.
Fluorine.
So we're really just going, which one wants to bond, wants to hold electrons around it the most?
Fluorine?
The answer is fluorine. Which one do you think is going to be the least?
Francium.
Francium, right? So that is our trend. Okay. As we move, as we get smaller, or decrease our in number, and as we add more electrons or protons across, we increase our electronegativity. Okay? We already talked about this. We said, hey, we got bonds, and we got ionic, we've got polar, and we've got nonpolar. Polar covalent bond, where they're different elements. And that is carbon and hydrogen. That's it. So if I have hydrogen, hydrogen, chlorine, chlorine, fluorine, fluorine, sodium, sodium, same electronegativities by definition. The only other two that I can put together like this is going to be chlorine and it's going to be carbon and hydrogen. Anything else is going to form either a polar or an ionic bond. Okay. All right. That's something I'm likely to ask you to know. Okay. All right. Saying all kinds of stuff, but it comes up to nothing. We're going to stop there. Let's address this. You got your calendars? Everybody got a calendar out?
Yeah.
All right. So, we're supposed to have class the 25th. I have international students who have already told me they're peacing out. They're not going to be here. So we're taking that into account. Your final is online anyways, okay? And we'll have an essay. I'll talk to you about that. I'll give you an essay prompt in advance, okay? The question is, what are we doing for your okay, you know that we don't have class on the 19th, okay? Yes, sir?
No, sir. It's just. That's not the question.
Okay. We are on the, I mean the 18th for us, sorry. So I see you guys today. I've got one, no time at all, basically. I see you, I can teach you 2 more days or 3 more days. That's the thing. So would you like a test in class or online? Now, it's going to be the same amount of material. The question is, do you want it to be taught in 2 days or in 3 days?
You get 3 if we do it online, 2 if we do it online.
3, you get 3 days of instruction if you do it online, and you get a window to take it in. Or you take it on the 20th, and everything's crammed into 2 days.
Yeah, I would say 3 days only.
3. Okay. So your third exam will be online. It'll be set up just like my other, I'll set it up exactly like my online class. You'll have a window to take it in over quite a little while. It won't be in a giant rush for you, okay? 3, 4, 5 days, something like that. The deal with that is I will put the test, I'll have a 1 problem test. The way it'll appear on one thing, it'll have all of the problems listed. My recommendation would be to print that out. I think that's the easiest way to go. You can handwrite out, or you can just write your answer, whatever you want to do. You know, what you've done, we're good. You do your work in the time period allotted, which is probably 1.5 to 2 hours. Okay? It'll be 2 hours. Because I know it takes time to print it out, to upload it and all that kind of stuff. It just takes longer when you're not in class, okay? Plus, you guys went over last time anyway, so I'll give you at least 2 hours. You do your test, you take a picture of all your work, multiple pictures probably, and you email it to me. I have a timestamp for what time you log in and start it, and I'll have a timestamp for what time you send your email. Okay, so I'll know that you were in the thing, and you know, that'll be how we'll go. All right. All right. So that takes care of that. This your last test will be online. All right. Okay. Any questions for me?
So we're gonna have class this Wednesday
Yes.
on the 20th and on the 25th.
Hold on 1 second. Do I have this moving backwards?
What will the 5 days email be open for, like around the 20?
Hold on. I may already be off, man. Okay, we have class the 13th. We don't have class the 18th because of the BMA stuff. I have class the 20th. Okay, so everything will be crammed into 2 classes, not 1.
Better.
All right.
Well, and the test will be open after them 2 classes.
Yeah, man, I'll open the tests, I don't know, like,
Maybe on all the week on the 25th.
yeah, I'm flexible.
When would the final be? Like,
That one I have to do, I think like December 2nd and 3rd or something like that.
Is that on like everything? Like, is that like a combination of tests 1, 2, 3, 4?
I haven't decided what I'm doing. I only know one part of it right now. All right, that's it. That's all I got.